Alright, continuing on with 11.2 and trig derivative applications. This is also our last day of notes for the unit. Yes. Woo! So that's exciting. Alright, two examples. First one. A sector with a central angle theta is cut from a circle of radius 12 inches. The edges of the sector are brought together to form a cone. Find the magnitude of theta so that the volume of the cone is a maximum. Okay, so this is an optimization problem, obviously, because we are trying to maximize something. Now, here we really need to get a grasp on what's happening. So, what's the first thing we like to do most of the time if we're able to? Draw a picture. Very good. So we're going to draw a picture. Start with a circle, right? Circle. We're going to cut out a sector from that circle. So this is my theta. I know this is 12. Now what's happening is we're going to cut out this sector, and then we're going to take this line and connect it to this line, so that what's left over becomes a cone. So if you can picture that, you might have done this back in like grade school or something. I don't know why, but probably, take like a doily, cut out a triangle, or a sector specifically, and then fold it together and you get a cone. So then we're trying to maximize the volume of that cone. So a few things we want to recognize that we need to know. Volume of a cone is 1/3 pi r squared h. Lateral surface area of a cone I'm going to use green because the lateral surface area of the cone is going to be represented by this area. So lateral surface area of a cone is pi r times the square root of r squared plus h squared. Then we're also going to be using area of a sector. So area sector is theta r squared over 2. And then we should know the area of a circle being pi r squared. Now, one thing to point out, notice that we have different r's here. The r in my volume equation is not going to be the same r in my area of a sector or area of a circle equation. So I have to be careful with that. So with this information, I want you to try to find the magnitude of theta so that the volume of the cone is a maximum. So you know that you're taking the derivative of the volume equation. Also, we want to get everything in terms of one variable. So if we were to draw another picture representing our cone, so I know in my cone this is h, and I know this is 12, and then this is the r that I'm referring to in my cone. So we're trying to maximize the volume of the cone with those variables. I know r squared plus h squared equals 144. So therefore h equals the square root of 144 minus r squared. Okay, so now with this information I've helped you hopefully get started. I want you to pause the video and try to solve this problem. Unpause when you're ready to check your work, or if you get stuck and scared and need help. Okay, So you should end up with the maximum volume of the cone will be when theta is approximately 1.153 radians. Easy enough, right? How do we come up with that? Well, this one was a little bit of work. So let's go back up to the top. So we already went through the equations that we're going to need to use, also recognizing that the lateral surface area and the area of the sector should add up to the area of the circle. So this recognition comes in towards the end of the problem, but I want to point it out now looking at this picture. That remember, the green here represents the lateral surface area of the cone when we cut out the sector. So if I leave this as a circle, that green plus the area of the sector, which would be the yellow here, would add up to the area of the circle. Okay, so again, that's going to come in toward the end. So we have our cone, where we know the slant height of the cone is 12, and then we have the radius of the cone and the height of the cone, and a relationship between those is that h equals the square root of 144 minus r squared. So now I rewrote the volume equation. That's going to be 1/3 pi r squared times h, which is the square root of 144 minus r squared. So take the derivative of the volume with respect to r. We have to use our product rule. So the derivative of the first is going to be 2/3 pi r times the second term, which is the square root of 144 minus r squared, plus the first, 1/3 pi r squared, times the derivative of the second. We have to use the chain rule. So I bring down the 1/2 times the inside, which is 144 minus r squared, subtract 1 from the exponent, so it's to the negative 1/2, times the derivative of the inside, which is negative 2r. Now this 1/2 and this 2 are going to reduce. R times r squared becomes r cubed. This term right here is going to become the denominator, and then the 3 is going to go with that. This just stays 2/3 pi r times the square root of 144 minus r squared. Now I want to get a common denominator because I need to find critical values. So in order to find critical values, I need to be able to set this equal to 0. I don't want to lose any of my potential critical values though, so I want to get a common denominator. So I multiplied the top and the bottom of this term by the square root of 144 minus r squared. I didn't need to multiply by the 3 because this already has a 3 as a denominator. So when I multiply this by the square root of 144 minus r squared, I'm going to distribute 2 pi r to the 144, so I get 288 pi r, and I'm going to distribute 2 pi r to the r squared, so I get minus 2 pi r cubed. The minus 2 pi r cubed and minus pi r cubed will combine to become minus 3 pi r cubed. So every term in the numerator has a factor of 3, a factor of pi, and a factor of r, so I took that out. Then this 3 is going to reduce with this 3. So we're left with, in factored form, dv dr is pi r times the quantity 96 minus r squared over the square root of 144 minus r squared. Now I need to set that equal to 0. So remember, when we do that, we find our critical values by setting the numerator and the denominator equal to 0. So I do pi r equals 0, 96 minus r squared equals 0, square root of 144 minus r squared equals 0. I get critical values of 0, plus or minus 4 root 6, plus or minus 12. Now I can eliminate almost all of those. I can eliminate 0, negative 4 root 6, plus or minus root 12. I'm sorry, this should not be a root, this is just 12. So I can eliminate plus or minus 12 because those are outside of the domain. And I get that by, well, 1, I should understand that I can eliminate negatives. If I have negatives, then this is not going to actually be a cone. If I have 0, this is not going to be a cone. And if r is 12, this is not going to be a cone that can be cut from that circle. So going back down here, the only one I have to test then is 4 root 6. So I use my increasing decreasing chart and I test 4 root 6. And since dv dr is greater than 0 on 0 to 4 root 6 and dv dr is less than 0 on 4 root 6, 12, at r equals 4 root 6 will be a max volume. So now I'm going to use that to find the lateral surface area. So the lateral surface area, I plug in r. This was the h term, so I just plugged in r for that. And I end up with 48 root 6 pi. The area of the circle is pi times 12 squared. Remember, this is a different r, so that's 144 pi. the area of the sector is theta times 12 squared over 2, which is 72 theta. But now this is what I was talking about. I know that the area of the sector is the area of the circle minus the lateral surface area of the cone. So this is the key connection, that I know 72 theta equals 144 pi minus 48 root 6 pi, and I can divide everything by 72. So that's how I come up with theta. So the max volume of the cone will be when theta is 1.153 radians. As always, round to 3 decimal places unless otherwise specified. Alright, last example. An airplane flying at 450 kilometers per hour at a constant altitude of 5 kilometers is approaching a camera mounted on the ground. Let theta be the angle of elevation above the ground at which the camera is pointed. When theta equals pi thirds, how fast does the camera have to rotate in order to keep the plane in view? So I want you to do this on your own. Draw a picture. The fact that the plane is approaching the camera should help you understand the relationship of the picture in the direction that you're going. And then I want you to find, in this case, d theta dt. Pause the video, unpause when you're ready to check your work. This one should be much shorter and easier than the last one. Okay, so we should end up with the camera will have to rotate at 67.5 radians per hour to keep the plane in view. I did not specify units, so radians per hour is fine. It's not really a practical measurement. Radians per second would probably be better in this case, but I didn't specify, so it's fine if you left it like that. Alright, here's our picture. I called this x, I called that y, I called that z, this is theta. Z doesn't actually come into play because I'm going to use tangent or cotangent. You could use sine or cosine and then z would come into play, but that's just more work. So I know dx dt is 450 kilometers per hour, or you could call it negative 450 kilometers per hour. It doesn't matter with the positives or negatives as long as you understand the direction. dy dt is not changing, or is 0 because y is not changing, I should say. So if you use tangent, it's actually a little bit more work. I'll show you what I mean. So tangent of theta is y over x. Y is a constant, so that's 5, so I can write this as 5 over x. If I take the derivative of tangent, I get secant squared theta d theta dt equals negative 5 over x squared times dx dt. So I need to know what x is when theta is pi thirds. So over here to the side, I did tangent of pi thirds equals 5 over x, and I solved this for x. I know that tangent of pi thirds is root 3, so x is 5 root 3 over 3. If I used cotangent, I would not have to ever find x when theta is pi thirds. I'll show you that after this. So now I solve for d theta dt, so I divided by secant squared of theta. I've substituted in all of the values that I know. So x is 5 root 3 over 3, so that's squared. Dx dt is 450, and then secant of pi thirds is actually 2, so this quantity squared is just going to become 4, so this is going to be 1/4. Type that into your calculator and it actually simplifies nicely to negative 67.5 radians per hour, but again the negative is just telling us how it's turning. Had I used a negative speed for the airplane, then this would have been positive. So it just, you need to recognize that that's the direction it's turning to keep up with the plane. So then we write our answer in a sentence. Again, had the units been specified, you might have to do some sort of conversion here. Okay, and then real quick just to show you, so had you used cotangent, you would have had cotangent of theta is x over y, which is x over 5. So now when you do the derivative, you get negative cosecant squared theta d theta dt equals 1/5 dx dt. So notice that the derivative never has x in it. Okay, so we want to make sure that we still understand related rates and optimization, because both of those are going to still play a major role in our calculus, and now we just have more derivative tools to help us with those types of problems.